Okay, so in this part of our video series, we're going to look at example 3, which uses the factoring process for quadratics combined with identities in solving trig equations like this one, 2 sine squared x plus 3 cosine of x equals 3. And if you notice on the side here of the foldable notes booklet in this example, I listed some steps for your reference for tackling problems like this. So step 1 is to use identities to rewrite the equation with only one type of trig function when possible. And here we've got both sines and cosines together in the same problem. And we can tell that since it's not multiplication, we can't use a product identity. There's no tangents, so we can't use a quotient identity and then try to find a least common denominator to combine them the way we did in example 2. So now we're going to turn to our trig hexagon and look for another alternative, for example, our Pythagorean identities. And remember, on the hexagon, those come from these 3 triangles. So we have a Pythagorean identity for sines and cosines with this top triangle that says sine squared x plus cosine squared x is equal to 1 in the center here. So if I jot that down just as a reminder, sine squared x plus cosine squared x equals 1. And again, we took that from this top triangle of our trig hexagon. We can rearrange that Pythagorean identity to get the sine squared x here by itself. So I would subtract the cosine squared x from both sides, and now sine squared x I can substitute in the equation using this identity 1 minus cosine squared x. So because that 2 in front is being multiplied, I'm going to need parentheses to group this binomial 1 minus cosine squared x when I substitute that Pythagorean identity. Then that's plus 3 cosine of x, and that's still equal to 3. So now to get rid of those parentheses, I'm going to go ahead and distribute, and I'll have 2 minus 2 cosine squared x plus 3 cosine of x equals 3. And here we can see that squared term. That tells me that everything is quadratic here because I have all cosines, all the same trig function, but I have a quadratic term and a linear term. That means that we're going to need to do some factoring or try the quadratic formula to solve this equation. So in either case, we need to start by getting it set equal to 0. So we're going to, since this is a negative here, move everything to the other side to get it equal to 0. So we'll add this 2 cosine squared x to the other side. We'll subtract over the linear term, the minus 3 cosine x, and then we'll subtract this 2. There's already a positive 3 here, so 2 minus 3 is a positive 1. And now our trig function is in standard form for a quadratic set equal to 0. It's usually easier for students to do substitution here to make it easier to look at when they're trying to factor. So to do that, I'm just going to pick a variable. Here I'll just call it, let's try u. So we're going to let u be equal to cosine of x. And now everywhere in this equation where I had a cosine of x, I'm going to substitute that with a u when I rewrite it. So 0 is equal to 2u squared. Instead of cosine of x, I put a u there, minus 3u, because instead of cosine of x, I substituted u, and then plus 1. Now, that step isn't required. It just, for most students, and for me, in fact, it makes it easier to factor without having those trig functions swimming around in the alphabet soup. So now I'm going to go ahead and use my crisscross and my box strategy that we learned earlier in the year to factor this quadratic. And If you have another factoring strategy you prefer, by all means use it. If you can factor it in your head, go ahead. But since I just want to make sure I cover all the bases here for people in the tutorial, I'm going to go ahead and factor this with the crisscross and the box, since the leading coefficient is greater than 1. So I multiply the outside, the a and the c, to go in the top of the crisscross. So 2u squared times 1 goes up here, 2u squared. Then I'm going to write the middle term in the bottom of the crisscross, and that's a negative 3u. And this organizes my thinking as I try to find factors of 2u squared that add to equal negative 3u. And those would be a negative 2u and a negative u, because negative 2u times negative u is a positive 2u squared at the top, but negative 2u minus u is a negative 3u when I combine them at the bottom. So those two values in that diagonal going this way, they go in my box in either spot. Those are interchangeable there. Then my first term here goes in the first box, the 2u squared. My last term, the constant, goes in the last box. That's a 1. And then in order to factor it, I'm going to go across each row and up and down each column looking for the greatest common factor. So across the first row, 2u squared and a negative u, they both have a u in common. Across the second row here, negative 2u and a 1, they have a 1 in common. Up and down the first column, 2u squared and negative 2u, they have a u in common and a 2 in common. Then the second column, negative u and 1, they have a 1 in common. Whenever the diagonal in that factor box is negatives, so I have a negative for both of those, each of my signs in the factors are going to be negative as well. So on the outside, here are the factors that go with my trinomial. So I have a factor of 2u minus 1, and then a factor of u minus 1 on the other side. Okay, and we can check that we factored that correctly just by doing a quick FOIL. So 2u times u, there's our 2u squared in the front. 2u times negative 1, and then another negative 1 times u, they add up to negative 3u in the middle, and then negative 1 times negative 1 on the outside, that's my plus 1 for the constant. So now we can see that that checks. Okay. So once it's factored, we can go ahead and put back the cosine of x. Remember, we pulled that out and substituted with a u just so we could make this a little easier to look at for the factoring. But now we're going to put it back. So instead of u, I'll write 2 and then cosine x minus 1. And in place of this u, I'll put in that cosine of x again and a minus 1. So now that we have factored this and it's set equal to 0, we can go ahead and use the zero product property and solve by setting each factor equal to 0. So 2 cosine of x minus 1 is equal to 0, and cosine of x minus 1 is also equal to 0. Okay, and those are two distinct problems that we want to solve one at a time. So I'm going to need a little bit more room here so you can see down at the bottom. There we go. Okay, so on this side, if I add 1 to both sides, then cosine of x equals 1. Then we'll divide, 2 cosine of x equals 1. We'll divide both sides by 2. Those 2's cancel, and cosine of x is equal to 1/2. So when we want to get the x by itself, we need to do the inverse operation to both sides. So x is equal to the arc cosine, or the inverse of cosine, of 1/2. So we want to find all of the angles on the unit circle where the cosine, which is the x-coordinate, is a positive 1/2, and that would occur here in the first quadrant at pi over 3. so pi over 3 is one of the solutions. Then we will have a second solution in the other quadrant where cosine is positive. So if we remember that acronym, all students take calculus, the A tells us that all 6 trig functions are positive in quadrant 1. The S reminds us that sine and its reciprocal cosecant are positive in quadrant 2. The tangent, the t here, tells us that tangent and its reciprocal cotangent are positive in quadrant 3. And then cosine and its reciprocal secant, those are positive in quadrant 4, which is where we want to be because we have a positive 1/2 as our cosine. So we already found this pi over 3 answer from quadrant 1. That's our reference angle. There's 2 pi radians in the whole circle, so this would be 6 pi over 3 along the positive x-axis. And so using that reference angle to get into quadrant 4, instead of going in the counterclockwise, the positive direction, pi over 3 from 0, I'm going to go backwards in the clockwise direction. That's my negative. So I'm going to be subtracting pi over 3. And 6 pi over 3 minus pi over 3 is 5 pi over 3. So my second solution is where x is 5 pi over 3. Okay, now we're going to look at this second possibility where cosine of x minus 1 is equal to 0. We'll add 1 to both sides, and we'll have cosine of x equals positive 1. Then again, to undo that cosine, we're going to need to arc cosine both sides. That's taking the inverse. So the arc cosine of 1 now is x. And looking at our first quadrant of the circle, remember the cosine is the x coordinate, and that value here at 0 radians has an x coordinate of 1. And that would, in the interval that we're interested in, because we're going from 0 to 2 pi here, in that interval those would be 0 radians and 2 pi radians. That's a quadrantal angle, and there is no other point on the circle where the x value is a positive 1. If we were to look at the negative x-axis, since that's a quadrantal angle, the x value would be negative 1, which would not check in this particular situation. So speaking of checking, now we're going to want to go ahead and put those answers into the graphing calculator and verify that they work. So in the mode, I'll turn it on first. So in the mode we want to be in radians, which it looks like we are. And then we'll clear the home screen, and we're going to store pi over 3 as the x value. Okay, then typing in the original equation, and remember this notation, sine squared x, does not exist on the graphing calculator. So to enter that in the equation, we're going to need to recall that the square is referring to the fact that the sine function is what's being squared, not the x. So we're going to enter 2 and then parentheses, and we have sine of x. We'll close the parentheses on that sine function, and then that's what's being squared, the sine of x. Okay, so that function gets squared. Then we're going to add 3 cosine of x, and to get to the equal sign, we go to second math to open the test menu. The equals is up here at number 1, and we want to check that that equals 3. So we type in a 3. And remember, whenever you grab the equals from the test menu, when you press enter, you're asking the question, does this check? When you substitute in pi over 3 for all of these x's, do we get a true statement? And the calculator will respond yes with the number 1, or no, it doesn't check with the number 0. So we press enter and we get a 1. So pi over 3 checks as a solution. Okay, now we're going to check the second answer, which is 5 pi over 3. So we type in 5 pi over 3, store x, enter, and instead of retyping that equation, we'll arrow up and press enter when it's highlighted to retype it automatically. And again, we get a 1. So 5 pi over 3 checks as a solution. Next, we're going to take 0 and store that as x in radian mode. Then we're going to grab that equation again, press enter, and it checks. Okay, then the last one, 2 pi, store x. We'll go back up and get the equation, press enter, and again we get a 1. And so all 4 of those are solutions to our trig equation, 2 sine squared x plus 3 cosine x equals 3 over the interval 0 to 2 pi.